Okay, so let me ask you this. Do you know how forests really help fight climate change?
It's a fundamental question, isn't it?
Yeah.
We know they're crucial. They pull carbon dioxide out of the air.
And they store it like these huge, enormous carbon warehouses.
Exactly. Gigantic warehouses. And quantifying just how much carbon gets stored in, say, a particular patch of forest, that's critical.
Right. It's not just interesting trivia.
No, not at all. It's, fundamental data. You need it for conservation planning,
Yeah.
for understanding climate impacts properly, even for things like carbon markets.
We call that the carbon stock, yeah.
That's the term. Yep. Carbon stock.
But okay, here's the thing I imagine. The amount of carbon, it isn't just flat across the whole forest, is it? It must vary.
Oh, absolutely. It varies a lot. You might have denser growth in one spot, maybe younger trees over there, different soil.
So the carbon density, how much carbon per square meter or whatever that changes.
Precisely. It's
Yeah.
not constant. So if you want the total carbon stock for a whole section, maybe a specific plot of land, you can't just measure one tiny bit and multiply it out.
Doesn't work like that.
Nope.
And this is where we get into the core of this deep dive, right? At using math to figure this out. How do you measure a total when the density is all over the place?
Well, the first step usually is trying to model that variation.
Yeah.
So researchers go out, they take field data measuring trees and sample areas, that kind of thing.
Boots on the ground.
Yeah,
Okay,
exactly. And they combine that with maybe remote sensing, data from satellites, drones,
Yeah.
to build a mathematical picture, a function that describes how the carbon density changes across the area you're interested in.
So instead of one number for density, you get a formula, like CX. If we
Yeah.
imagine maybe walking a straight line through the forest, CX tells you the density at any point X along that line.
That's the idea. Now, real-world functions are obviously way more complex. They might have multiple variables or they're statistically derived. Very messy.
Sure.
But let's use a simple example just to see how it works. Imagine along that line, maybe the density follows something like CX equals 2x plus 5.
Okay, 2x plus 5. So the density changes linearly as you move along the line x.
Right. It's just a model, but it illustrates the point.
Got it. So now we have this function, cx, describing density at each point. But we want the total carbon for a whole stretch, maybe from where we started, equals 0, out to, say, 10 units away, x10. How do you get from the density at points to the total amount over that whole stretch?
And that is where calculus comes in, specifically integration.
Okay. Integration.
It's the mathematical tool basically designed for exactly this problem, adding up a quantity that's changing continuously over some kind of interval or space.
So it's kind of like summing up the carbon contribution from every single infinitesimally tiny slice along that line from 0 to 10.
That's a perfect way to visualize it.
And the amount in each tiny slice is given by our density function, Cx.
Exactly. So when we calculate the definite integral of our function in our simple example, that's t-shares 2x plus 5 dx, what we get out is a single number.
A single value.
Yep. And that value is the total estimated carbon stock for that 10-unit line segment, according to our model.
Okay, so the math gives us a concrete number. Tons of carbon, maybe? What do people actually do with that number then in the real world?
Oh, it's incredibly useful, that total stock number.
Yeah.
It lets conservation groups set a baseline. They can monitor if the forest is gaining or losing carbon over time.
Right, tracking changes.
It helps decide on land management, like where would protecting land have the biggest carbon impact?
Yeah.
And it's absolutely essential if you want to participate in carbon credit programs. You have to quantify accurately.
So it takes this general idea of forests are good for carbon and turns it into hard data for policy, for economics.
Precisely. Verifiable data. It connects the ecology directly to decision making.
And I guess in reality, you're not just looking at a line, right? You need the carbon over a whole area or even like the whole volume, including soil.
Absolutely.
Yeah.
The same idea just scales up. You use multivariable calculus integrating the density function over 2 dimensions for an area or 3 for a volume.
It's more complicated mathematically, I bet.
The math does get more complex, yes, but the core concept, it's the same. Integration is still just summing up that varying density to get a total.
It's really fascinating seeing these, fairly abstract math tools like integration being so vital for tackling huge, urgent problems like climate change.
It really is. It allows
Yeah.
us to translate these incredibly complex natural systems into numbers into metrics that scientists and policymakers can actually work with.
So next time you think about forests helping the planet, you can remember there's some pretty powerful math going on behind the scenes to figure out exactly how much help they're providing.
Yeah, that integral sign we just talked about,
Right.
that could literally represent tons and tons of carbon locked away, working to stabilize our atmosphere.
It really shows how everything's connected. Field work, data science, calculus,
Hmm.
all working together. Math isn't just equations, it's a language, a tool we use to understand the world, measure it, and hopefully protect it. Makes you wonder, what else could we measure and manage better if we really applied these tools? Something to think about.